up. So it's a pleasure for me today. I'm going to introduce you to our seminar speaker today. I've not known Chris very long, Chris Piecuch, who's currently an assistant scientist at the Woods Hole Oceanographic. And we met last year. There was a sea level conference in Norfolk, sponsored by Clivar. And a lot of you will remember my next to last PhD student, Phil Thompson. And Phil and I were on the organizing committee, so we had a working dinner one night. And we finished the dinner, and Phil, I call him Kid, he calls me Pop. So after we finished the dinner, he said, you know, I'm going to go meet up with Billy Sweet and Chris Piecuch and have a beer. So why don't you come along? And I figured, wow, this is sweet. The kids are inviting Pop out for a beer. Isn't that wonderful? I'm going to leave it at that. I'll just tell you that 3 or 4 hours later, I was wondering what was I thinking, but we'll leave it at that. Chris has a really interesting background. I really enjoyed putting together this introduction. He did a bachelor's degree at URI in 2006 in physics, mathematics, and German language and literature. I didn't realize, was that a minor or a major? But anyway, a very interesting undergraduate background. And then what was also interesting, and I have another small world story I told Chris earlier, is he then spent 2 years in the Peace Corps. And the small world story is the last person I invited to have a seminar, it's been quite a while back, was Brian Arbick, who also did 2 years in the Peace Corps after being an undergraduate. So there's something about me picking out seminar speakers. I don't know what the connection is, but there's something going on there. But anyway, very, very impressive. He then returned to URI and did a master's degree in biological oceanography. And I asked him what was up with that. And he said, well, I had to come back to the physics. And I said, you mean you left the dark side, of course? And he said, no, I had to do it because I really sucked at biology. So I'm sorry, but that's a quote. And but at any rate, in that time after the master's, though, he went to work at AER. A lot of you know Rui Pont's location, worked with Rui and did a lot of the work that ultimately was comprised his PhD from the University of Rhode Island again in physical oceanography. And we're really pleased that he came back to us. And Chris is going to talk to us. Oh, you all saw the title. He's going to talk to us about some observations he's been making with sea level to look at changes in the Gulf Stream and then the meridional overturning circulation. So Chris, please.
Great. Thanks so much, Gary. I appreciate that. Very kind and somewhat embarrassing introduction. Also want to thank Gary more generally, and also Amelia for giving me the invitation to come talk to you all. So you guys should be seeing my screen now. Yeah, it's really too bad that I was not able to come down to CMS in person. Originally, I was supposed to come down in the spring, but as we all know, the state of the world has changed. So a virtual meeting will have to do. Yeah, as Gary said, I'd like to take the time today to talk to you about a paper I recently published. So I want to tell you that story. But before I begin, I want to really encourage you to interrupt and ask questions. So this is going to be a pretty interdisciplinary talk. By the title, you probably understand that there'll be some elements of physical oceanography and ocean circulation, also some elements of sea level science. I will try not to get too deep in the weeds, but this will also involve elements of what might be called probabilistic data assimilation and also elements of uncertainty quantification. All that being said, there's something here for everyone in the sense that you'll probably encounter something during my talk that you're unfamiliar with or maybe you don't understand. So I really do want you to come away with the essence of the story. So please don't be shy, ask questions. I kind of let the cat out of the bag with my title in the sense that you know where I'm going with this story. So I thought I would just go whole hog and give you all of my conclusions right from the beginning. So as you could probably tell from the title, I infer based on observations that the Florida current, so this is the Gulf Stream at Florida Straits at 27 north, the Florida current transport likely weakened over the past century. That observational conclusion corroborates independent hypotheses, largely based on proxy records, that the deep return flow of the Atlantic meridional overturning circulation has declined in the recent past. Also, my conclusion based on observations lends support for simulated relationships in climate models between changes in the deep return flow of the overturning circulation and coeval changes in the western boundary current. So those are the main, if you don't come away with anything else, you can leave with these conclusions. So let's get to the talk. So if you couldn't tell from my previous slide, the big umbrella topic here is the Atlantic meridional overturning circulation, or what I'll call AMOC for short. So the AMOC is this blanket term that is used to summarize the complex behavior collectively of North Atlantic Ocean circulation. I'm giving a cartoon schematic of what I mean here on the right. I'm using these red arrows to illustrate the general northward movement near the surface of warm and salty waters to the northern North Atlantic. When those warm salty waters reach the far northern latitudes, they encounter conditions that are favorable to buoyancy loss, to densification and sinking. Okay, and those are indicated by the yellow dots and lines. And once at depth, those denser waters on the whole flow back equatorward, forming something of a loop, or you might have heard it called a conveyor belt. I'm, of course, drastically simplifying the complex nature of Atlantic circulation, but this is sort of a big picture kind of notion. And lots of people are interested in this notion of the AMOC. Certainly to physical oceanographers and climate dynamicists, the AMOC has been implicated in both the variability and stability of the climate system, but also abrupt climate change events in the paleoceanographic record. As I'll discuss, the AMOC has some relevance for understanding sea level at the coast. And even if you're not a climate dynamicist or a physical oceanographer, AMOC is relevant for things like for carbon cycling and ecosystem productivity. So suffice it to say, there are lots of reasons that we, as marine scientists more generally, want to know about the past behavior, how the AMOC has changed. But we very soon encounter a challenge in the sense that, as many of you in the virtual room probably know better than I do, it's very difficult and expensive to observe large-scale ocean circulation, especially at basin scales for a long period of time. So here I'm showing some figures from a recent review paper by Elner Frackel-Williams last year, discussing the state of the AMOC observing system. So on the left here, we have this map of the Atlantic, and in each of these colored lines nominally indicates where there is a long-term observing array of the overturning circulation, going from the OSNAP array in the far north to the Samba array in the south. Okay, and for a few of those observing systems, I'm showing the corresponding AMOC transport time series on the right. So we have years on the x-axis at the bottom, and we have the transport in units of sphere drips on each of these individual y-axes. There's all kinds of stories I could dive into about this plot, but what I really want to get across here is a really simple fact, which is that if you look at the x-axis, the span of time is really short. These records are years, at most 2 decades long in the case of MOVE. Now, don't get me wrong, these long records are a phenomenal achievement in the context of ocean observing. But for those of us interested in the longer term evolution of the climate system, records of this length simply aren't long enough. So what do? Well, we turn to proxies. And by proxies, I mean either other elements of the climate system or natural archives that show a systematic relationship to the overturning, so that even though we lack long instrumental records of the AMOC per se, we can look to other records to give us some sense of what's happening. Just to give you a sense of proxies, I'm showing some model results here from Cesar et al. In a paper published in Nature a couple of years ago. They're illustrating this notion of a proxy, okay? So each of these dots shown here on the scatter plot is a result from a different climate model, okay? And on the y-axis, on the vertical, these authors are showing the change in the AMOC stream function. So this is how much the AMOC stream function will change in a future global warming scenario. Okay, so this is the AMOC change on the y-axis. On the x-axis on the bottom, you see indicated this AMOC index change, and the units are Kelvin per century. Okay, what Cesar and colleagues mean here by AMOC index, they mean the sea surface temperature in the subpolar North Atlantic. Okay, so what this result is showing us here, at least in model world, is that when you have a change in the AMOC stream function in the North Atlantic, that is highly correlated with a change in the sea surface temperatures in the northern North Atlantic. The idea here is that you can use then the sea surface temperature records, which are longer, to make a statement about the AMOC. Okay, of course there are questions that arise here. One can ask, okay, what are the, if there is truly this relationship between the AMOC and SST, what are the physical processes that mediate this relationship? Even more broadly, how much do we believe the climate model's ability to simulate observed reality? All those questions aside, folks who have published papers like this are arguing based on the proxies that indeed there has been a change, specifically a weakening of the deep return flow of the AMOC over the recent past, either over the past century or earlier, say at the end of the Little Ice Age. We want to test this hypothesis. We're going to take these results from past proxy-based studies as a hypothesis that I want to test. So here you can view my study as testing the hypothesis that the deep return flow has slowed in the recent past. So how are we going to do that? Well, I would like to appeal to mass conservation. What I mean by that is this: if we imagine a slowing of the southward deep return flow of the overturning, that change can't happen in isolation. It doesn't happen in a vacuum. If the deep return flow slowed, there must be some other element of the ocean circulation in the Atlantic that also changed to compensate it. Otherwise, you'd get this unrealistic and unphysical piling up of water in some regions of the ocean and an ever decreasing amount of water in other regions, which we don't observe. So there must be some compensating change. And the question becomes, if the deep AMOC is changing, what other elements of the Atlantic circulation are also changing? There's a lot of candidates. It could be the interior so-called spare-drip gyre circulation driven by the winds. It could be the Florida current. It could be the Antilles current. There are lots of possibilities, okay? Here's a hypothesis from climate models. So Beadley and colleagues sought to address that question. If the deep AMOC slows, what else changes? Okay, in the interest of time, and I'm actually not going to go through all these plots. I want you to all focus just on the far right plot here. Okay, similar to the last plot, Beadley and colleagues are looking at a bunch of different climate models, okay, a multi-model study, and each of the colored symbols represents the result from a different climate model, okay? Looking at this far right panel, on the x-axis, you see this quantity delta deep. This is the change in a future climate modeling scenario in the deep return flow of the overturning circulation, okay? That's the delta deep quantity. And in this far right panel, they're plotting delta deep against, on the y-axis now, this delta WBC. This is the change in the western boundary current in that same model over the same time. And what you observe very simply is a strong correlation. So Beadley and colleagues conclude that when you have a weakening of the deep return flow of the AMOC, that tends to be, at least in the models, and at least on centennial timescales, accompanied by a weakening of the western boundary current. Okay, so that's a hypothesis that we're going to use here. It's based on the models. We might question it because maybe the models don't have the horizontal resolution to properly simulate the physics of western boundary currents, but we'll take it as a hypothesis, and we're going to use it along with our previous question. So given the model hypothesis that when you have a weakening of the deep overturning, the western boundary current also slows, I can use this to test my hypothesis that the deep overturning has in fact slowed. In other words, I'm going to ask this question: has the subtropical North Atlantic surface western boundary current weakened over the recent past? And by the subtropical North Atlantic surface western boundary current, I mean the Florida current. I mean the Florida current, which is the headwaters of the Gulf Stream. So here we're getting into the study region. So here I'm showing two maps. Let's look at the left map first. This is the western North Atlantic region. It should look familiar to most of you virtually down in Florida. Don't worry for the moment about these squares and circles along the coast. These are tide gauge records. We'll get to that eventually. I want you to look for the time being at the color shading. So the color shading is showing time average surface speed deduced from drifters. Over most of the ocean, you see this deep blue or maybe light blue indicating slow or moderate flow speeds. But once you get into the Gulf of Mexico, specifically between Cuba and Florida, you see emerging this bright yellow snaking thin band, which is, of course, the genesis of the Florida current and what eventually becomes the Gulf Stream as it moves north along the South Atlantic Bight. The study region I'm interested in is here on the left. This is the Florida Straits. So now we're looking at the right panel, which is the zoomed in plot. Color shading on the right is now indicating depth, not speed. And what I'm indicating here is that the Florida Straits are very narrow, about 100 kilometers across, and very shallow region, about 800 meters or so at their deepest. So you have this very powerful current in the Florida current passing through a very narrow, shallow constriction. Okay, and this is our study region. I've labeled some regions of interest here. The black lines are locations of historical hydrographic and other data of the current, but I want us to focus specifically on these two thicker red lines I've drawn between roughly West Palm Beach and Grand Bahama Island. And I've given a gray arrow here called cables. So here, these two red lines mark the location of historical measurements since 1982 of the Florida current transport. And I won't go into too much detail, but it's sort of an interesting story here that these measurements, which are quasi-continuous and available just about daily since 1982, are made by means of abandoned submarine communication cables. It turns out that due to electromagnetic theory, the movement of charged particles in the ocean in the context of Earth's magnetic field, you can actually infer changes in the transport through Florida Straits by changes in the voltage on either side of these cables. So, but I'll defer the details there. So this is what the data look like. Remember I said we've got these Florida current transport data since 1982. That's the blue curve here. So again, we have time on the x-axis going back to about the early 1980s. Again, the blue time series is transport. The vertical bars are a standard error. And the ticks are on the left here. So we're going between 28 and 36 spare drips. Remember the question here. The question is, has the Florida current undergone long-term change that would corroborate this story about the deep overturning? Well, if we're looking at just these data, it's clear to me that there is year to year and decade to decade variability that's measured by these cable transport data. But it's not obvious, at least not obvious to me, whether there's any real meaningful long-term change that's obvious in these data. So we're making some progress here. Remember the earlier slide where I showed all of these AMOC observing systems that went back just a few years or at most 20 years. Okay, now we've got a time series here that goes back to the early 1980s, older than me and almost 40 years long. But this still isn't long enough to get to those questions of centennial or even really multi-decadal change in the North Atlantic circulation that we're interested in. This is where some proxies come in handy here. So I haven't just shown this blue time series, but overlaid is this orange time series. So this orange time series is a time series of sea surface height from altimetry. So specifically, I've computed the difference in SSH, sea surface height, between Grand Bahama Island, so this is on the east side of the Florida current, and around Miami, which is on the west side of the Florida current. And that's the time series shown here in orange, and the units here are centimeters, so we're looking at plus minus 16 centimeters. And the important point here is that the orange and blue time series, over the period where they overlap, are highly correlated. If you just sort of computed a correlation coefficient here, it's about 0.7. Okay, so the idea here is that you have a strong correlation between the Florida current transport and the difference in sea surface height across the current. Okay, this is encouraging, but it's not really a surprise. You expect a relationship like this from basic ocean dynamics. I was having a great conversation with some of the CMS students earlier today, and that session ended with Ryan asking me a really great question that really stumped me that I hadn't been asked before. She said something along the lines of, what was in our field, what was the biggest discovery that allowed your work that you're presenting on today to take place? And I was sort of quiet for a bit, and I thought about it, and I said, well, it's geostrophy. This whole study I'm showing is based on the simple notion of geostrophy. So geostrophy is very useful. So I'm showing here on the bottom right, I'm showing a certain form of geostrophy or thermal wind more correctly. And I'm saying here that T, which is the transport of the current, is proportional to this difference in zetas, zeta E minus zeta W, that's indicating sea surface height on the east minus sea surface height on the west. It's proportional by this factor of GH over F, where G is gravity, F is the Coriolis coefficient, the Coriolis parameter, and H is something like a scale depth. So very simple ocean physics, namely geostrophy and hydrostatic balance, lead to the expectation that these two quantities, transport and sea level difference, are related. So now, this is helpful. Altimetry is not going to help us out too much because altimetry only goes back to the early 1990s. But I know I said not to worry about it then, but if you think back a couple of slides, I showed you all these tide gauge records, okay, these coastal tide gauge records, which are much longer than altimetry, and in a lot of cases, much longer than this nearly 40-year Florida current measurements. What we're going to try to do, the essence of what I'm going to try to do here, is to use coastal sea level measurements and exploit these basic physical balances to try to say something about the long-term behavior of the Florida current, again, based on coastal tide gauge records. But we need to tread lightly and cautiously here, because while simple ocean physics leads us to believe that there's this relationship between transport and sea surface height, tide gauges actually don't measure sea surface height. They measure what's called relative sea level. Now, relative sea level, for those of you who don't know, it's sea surface height minus any movement of the land itself. Remember, tide gauges are situated on the solid Earth, and they measure sea level relative to that point. So you can measure a change in a tide gauge either due to sea surface height changes or due to vertical land motion. So we need to be aware of the many geophysical and otherwise isostatic processes that occur in the Earth system that are unrelated to ocean dynamics, the thing we're interested in, but can cause sea level change as measured by a tide gauge. I'm giving a couple examples just to give a tangible taste of this here. So I'm giving an example of two isostatic processes which can influence sea level at a tide gauge but are unrelated to ocean circulation. One is on the left, something that many of you might be familiar with, what's called glacial isostatic adjustment, or what's sometimes called post-glacial rebound. These are words for the ongoing viscous response of the solid Earth to the last deglaciation thousands of years ago. The Earth is still responding to that ancient ice. And what I'm showing here in colors is the rate of contemporary sea level change due to that process. So just to orient you here, so if we look over, say, northern Canada and Hudson Bay, we see these deep blue colors indicating sea level fall. Sea level fall because the land in that region is uplifting. These are the regions where the ice sheet was centered 25,000 years ago. That ice sheet, that Laurentide ice sheet, has since melted away, and so the area is no longer loaded down by that mass, so it can uplift. So by the uplifting solid Earth, you have a sea level fall. You get exactly the opposite in this band of yellow, sort of ringing around northern Canada, around, say, the U.S. East Coast and parts of the Labrador Sea. These are regions of enhanced sea level rise. These are regions that were along the so-called peripheral forebulge of the Laurentide ice sheet. These are regions that were not covered in ice, but were around the edge, and which were actually levered, or you can think kind of seesawed up due to the movement of mantle material during the last ice age. That mantle material, because Hudson Bay is no longer glaciated, that mantle material can move back towards Hudson Bay, which is causing this enhanced subsidence or land sinking, resulting in sea level rise. Okay, so again, lots of details, but the essence is here's a process that's ongoing that will cause sea level rise, patterns of sea level change unrelated to ocean circulation. On the right is another example. So this is related to a much faster response time, sort of an elastic response. This is the pattern of sea level rise expected from the ongoing melting of the Greenland ice sheet. Here I'm showing this in units of a percentage of the global average change. So in addition to weighing down Earth's crust, these ice sheets are very massive and have a large gravity field associated with them. So they actually have the ability to pull water close to them. Okay, so when you melt an ice sheet, you reduce that gravitational field, and it turns out that sea level, perhaps counterintuitively, actually falls around the ice sheet. And that's what's being illustrated here. The deep blues around Greenland, it'll indicate that sea level fall. The black contour is the line of no sea level change. So when you melt the Greenland ice sheet evenly, you get, say, no sea level change in parts of southern Hudson Bay and in the Gulf of St. Lawrence, for example. And you get enhanced sea level rise in the southern hemisphere and in parts of the Pacific Ocean. Again, I don't want to dwell too much on the details, but the point here is that there are lots of ongoing processes that cause sea level rise unrelated to circulation. So this is kind of a signal to noise problem. If we're going to use the tide gauges to say something about circulation, we have to be careful that we're not confusing those ocean dynamic signals with these isostatic geophysical processes. So that's one challenge we face in using the tide gauges. Another is the data themselves. I'm not sure if any of you in the room have actually worked with tide gauges. I know some of you have, but they're a very messy data set. They're very, I'll say it this way, they're very heterogeneously distributed in space and time. There are clusters of data in some regions and a complete absence of regions in others. There are certain times when there are more data than others. I'm trying to illustrate that with these two figures here. So on the right, I'm repeating this plot of the study region. Again, the circles and squares are the locations of historical tide gauge records. And I picked out a few of those locations and indicated them in color, kind of using them as example sites. And to the left, in sort of a color-coded sense, I showed the respective sea level time series from those example sites. Okay, so on the left we have sea level in units of meters on the y-axis, and I'm giving them relative to an arbitrary offset of about 7 meters. So don't worry about the absolute numbers here, just the change. And time on the x-axis. Now, in some places you have nice, long, mostly complete records. So for example, if we look at the green and the light blue time series here, these are the records from Key West and Fernandina Beach in Florida. These are, again, long records that go back about a century or so. Okay, but remember our goal here. We're trying to exploit geostrophy to say something about the Florida current. So we're really interested in sea level on opposite ends of the current. So around the Miami, West Palm Beach area and the Grand Bahama Island region. So which I'm indicating those. If you look on the right map around West Palm Beach and Miami, I have the yellow dot and the orange, and you can't really see it, but a deep blue dot. Those time series are very short. I'm showing those on the left. They're at the bottom right of the time series plot in a little bit of a bold color. Those data have a lot of gaps, and they're really short. At most, they go back to the mid-1970s, which, remember, we have these cable data since the early 1980s. So extending that back, 5-7 years isn't too great. Not really worth the effort. But hope isn't lost. The fact that I'm going to try to exploit here is that sea level is not a completely random field. It has correlation in both space and time. What do I mean? Let's look back at the light blue and green time series. Again, these are the sea level records from Key West and Fernandina Beach. Now, these are separated by hundreds of kilometers, and they're on opposite sides of Miami and West Palm Beach. But if you look really close, there's a fair bit of correlation in time between these series. So for example, if you sort of follow the two time series by eye, you see they both sort of peak just before 1950, and they drop dramatically, and they show a lot of the same interannual and decadal changes. This is showing us that sea level is a spatially coherent field. Similarly, it shows correlation in time. So what we're going to try to do is exploit the fact that sea level isn't random, but it shows spatial and temporal structure to try to fill in the gaps where there are gaps in the tide gauge data. I've used about half my time on a very long introduction, but I think it's important. Okay, so now you have sort of the background you need to understand my results. What am I trying to do? Well, I have two different data sets. I have almost 1,400 gauge years of yearly average relative sea level from 46 tide gauges along the southeast coast of the U.S. and over the Caribbean. These are taken from the Permanent Service for Mean Sea Level in the UK. I also have 37 years of annually averaged transport of the Florida current inferred from those submarine cables since the early 1980s. So these are my two data sets. And I've got two sort of coupled goals here. As I just hinted, I want to exploit the fact that sea level varies coherently in space. Sorry. I want to use the fact that sea level varies coherently in space and time to try to fill in the gaps. In other words, take what is a very gappy data set and make it a full, complete data set so that at every one of these 46 tide gauges, I have a complete time series of sea level over the past 110 years. Simultaneously, I want to use those sea level estimates in tandem with the cable data to estimate the current changes over time. Okay, so that I have a full, complete estimate of the Florida current transport for the last 110 years. Okay, so those are pretty lofty goals. How I'm going to do it? So this is my really only really technical slide here. So I'm going to walk through it a little bit slowly. I'm not going to get too deep into the weeds, but I do think it's important to give you the overall philosophy. Okay, I'm going to use what would be called either Bayesian data analysis or probabilistic data assimilation. The essence here is that the scientific problem I've taken on, trying to reconstruct the Florida current, it's a complicated problem with a lot of sources of uncertainty. And I'm going to take what is a very complicated, messy problem and try to break it down into more manageable, tractable pieces. I'm going to separate questions of the physics from questions of the data themselves, for example. So just to give you a sense, I'm going to abstract a little bit. Okay, what I'm doing in a sort of general sense is I have this imperfect data set, which I'll call symbolically Z. Collectively, this is the tide gauges and the Florida current. Okay, and these data are imperfect measurements of some oceanographic process that I'm interested in. Okay, here's sea level and Florida current transport. Okay, and the evolution, the change in space and time of sea level and transport, and the relationship between those quantities and the data, I can imagine being governed by various parameters, things like temporal variance or spatial scales or error covariances. Okay. And what I want to do is this. I'm given the data Z, okay, and I want to say something about the processes Y and these unknown parameters theta. It turns out that a mathematically coherent way to do this is through Bayes' theorem or Bayes' rule. So something that we probably all learned in an undergraduate or graduate level introduction statistics class ends up being really helpful here. It actually formalizes the scientific inference problem. So I'm showing Bayes' rule, or a certain form of Bayes' rule here on the bottom left. What I'm trying to do is make this what's called a posterior inference. Okay, I want to know the probability of the process y and the parameters theta given the data z. Okay, and the way we do that by means of Bayes' rule is by what's broken down on the right. I break this down into what I'm calling a process level. This is where all the physics is embedded. Okay, what are the odds that the process, sea level, or transport will evolve in a certain way, given the parameters? I want to separate that from what I'm calling the data level. What are the odds of observing the data as they are, given the process? And finally, how well do I know these parameters? Okay, so what this gives me a set of 3 different equations that I write down. I can, on paper, write down a set of equations that describe the physics. How does sea level change in space and time? How is sea level related to transport? Okay, that's separate from what I'll call my data or measurement level. Okay, that is to say, how does a biased or gappy measurement from a tide gauge correspond to the unobservable sea level process? And then finally, what I'll call a prior or parameter level. How well do we know these various parameters that govern the relationship between the data and the process itself? Again, a bit technical, but again, if you come away with one thing from the slide, just know that Bayes' rule affords us a mathematically coherent way to break down the problem into easier to manage chunks and to come up with a mathematically coherent results. So enough of that. This is the essence. So again, I write down these equations, I specify the models for sea level, the current transport, the tide gauges, the cable data, okay? The model does not have an analytical solution. You have to evaluate it numerically. So for those of you who have done problems like this, I use Markov chain Monte Carlo, specifically a Gibbs sampler. Those are all technical things. The essence is this. What comes out of this model is this very information-rich end product. I get a totally probabilistic estimate of transport change. So it's a probabilistic ensemble. In other words, what comes out isn't just an estimate of, say, the mean and the error, things like this. No, I have an ensemble of thousands of members, thousands of possible transport histories that are all equally likely given the available data and the model physics that I specify. Okay, so this will be really helpful for doing some very advanced hypothesis testing. So here's the most important slide, I think, of the whole talk. This is my probabilistic estimate of the Florida current transport over the past 110 years. Okay, so we're showing transport in units of spare drips on the y-axis, time going back to the early 20th century on the x-axis, showing a lot of information here. So let me walk you through what's going on here. The orange, I'm showing those cable measurements of transport that I showed earlier. Those are 1982 and onward. Again, the vertical bars are the standard errors. All of the different blue symbols are different facets of the probabilistic reconstruction. The thick blue line is probably the most familiar concept. This is the median or best estimate of transport over time. Okay, so that thick line is the median, or it turns out the mean over time. Okay, the light blue shading is a measure of uncertainty. This is what we might call the ±2 sigma level, or the 95% confidence interval. In the parlance of Bayesian analysis, you don't call it a confidence interval, you call it a credible interval, but for all intents and purposes, you can interpret it as the same thing. Okay. An important point to note is that the shaded 95% credible interval is what's called pointwise. This is a local measure of uncertainty. In other words, the way you interpret the shading is that if the estimates of error are meaningful, that there's a 95% chance that in any given year, the true transport falls between those bounds. Okay, a 95% chance that at that year, the true transport falls within that bounds. That's a local measure of uncertainty, but you can imagine saying something about uncertainties more globally. Okay, and that's what I'm showing here by these dashed lines, which are a bit wider. Okay, these are what's called the pathwise 95% credible interval. This is not making a statement about any given year, but it's giving a sense of the full 110-year trajectory of the Florida current. These lines mark such that there is a 95% chance that the Florida current transport never ever in any year strayed outside those bounds. Okay, and finally, the thin solid lines are two randomly chosen ensemble members. Remember, I said I have an ensemble of thousands of possible transport histories. I'm just showing you two randomly chosen ones here, just to give you a sense of what the solution looks like. Okay, that's what's going on here. So let's walk through a few things. So if we look at the period since 1980, there's excellent agreement between the observations and the model. Not too surprising. The errors that the probabilistic model gives are pretty much in agreement with the instrumental errors on the data. This is just returning essentially what I've told the model is that the cable data represent reliable measurements of the process. But immediately as we go earlier than 1980, we see the errors grow larger, and in fact, they grow roughly linearly in time. Okay, this is because we no longer have the cable data earlier than 1982. The inference is mostly based on those tide gauges, which have a more uncertain relationship to the transport. Okay, other things we notice, there's of course some substantial interannual and decadal variability. You can ask all kinds of questions about relationships to large-scale modes like the North Atlantic Oscillation and the Atlantic multi-decadal variability, etc. But really the most salient feature here that I want to look at is that it looks like, although however subtle, that there's a long-term decline in this transport. Let's look at that a little closer. Okay, on the left, I'm showing histograms. So these are sort of probabilistic estimate of the transport over 3 different periods. So the blue histogram on the left is the time average, 1909 to 2018. We find a 110-year average transport of 32.6 spare drips plus or minus 1.4. And all the plus minus values are 95% credible intervals, unless I say otherwise. That's the blue histogram. If we look at the period before 1982, so 1909 to 1981, slightly higher value, 32.9 plus or minus 2.1 spare drips. And if we look at the value since 1982, we see a much steeper yellow histogram reflecting much more certainty. Average transport is 31.8 plus or minus 0.1. Why am I saying this? Because it turns out that in about 85 or 86% of the cases, that transport since 1982, that skinny yellow bar, is actually less than the transport prior to 1981. In other words, the last 40 years, the transport has been weaker than the 80 years that preceded it. Okay, again, this is a suggestion that it's weakened. We can be a little bit more direct in this question about a decline. On the right, I'm showing another histogram. This is the histogram of the 100-year trend. Okay, so the value for the 1909 to 2018 trend is minus 1.7 plus or minus 3.7 spare drips per century. You can interpret that as indicating an insignificant decline. I think it's more helpful to sort of look at this in a sort of deeper probabilistic sense as saying in 82% of the cases, the transport declined. In other words, there's an 82% chance that the current declined over this 110-year period. So if you want to adopt this IPCC-like language, it's likely that the transport declined over the 110 years. Oops. So you might ask, how much does that conclusion, the Florida current has declined, how much does that conclusion depend on the particular time period I've looked at, 1909 to 2018? Well, here I've tried to address that question. Here I've shown the change in transport over every possible pair of decades. So not just 1909 to 2018, but any possible starting and end point. So what I'm showing here on the x-axis is the starting period, and on the y-axis is the starting period, and on the x-axis is the ending period. And I'm using colors here to indicate the blue-yellow shading to indicate how much the current has changed. So blue colors indicate that the current has declined, and green-yellow colors indicate that it has increased. And I'm giving these gray squares at any time that the change is not statistically significant at the 68% level, so plus minus 1 sigma. Really, the most important point here is that you see a whole lot of blue. In other words, if you move away from the diagonal, that is, if you choose a start and end point that are separated by more than just a couple of decades, so you start looking at, say, 40, 50, 60-year periods, if you choose a period away from the diagonal, you find statistically significant declines in the current, almost universally, okay? For example, that black dashed line, everywhere to the bottom right of that is a period 50 years or longer, okay? In that sort of bottom triangle, in 92% of the cases, in other words, 92% of start-end pairs, there's a significant decline in the current. Okay, so the point here is that there's nothing special about the 1909 to 2018 period in terms of the result. Pretty much any period you pick, provided that you've given yourself a few decades, the Florida current has declined. So it's a very robust result that the Florida current has declined fairly steadily over the past century or so. Let's keep sort of harping on this theme and try to ask this question another way. You can imagine, instead of fitting a trend or looking at differences between decades, you could ask, well, when was the current its weakest? Okay, and because we have a whole ensemble of estimates, we can calculate something like this. So what I've done here, I'm showing some more histograms, and again, I'm asking the question, at what point during the last 110 years was the current the weakest, and when was it the strongest? How do I do that? Well, remember, I have thousands of time series. What I'm going to do is I'm going to cycle through all these time series individually. And for each individual time series, I'm going to find the point on the transport time series, the point where transport is the weakest. And I'm going to store that year. Okay, and I'm going to do the same thing for the next year and the next year and so on until I go through all of the thousands of ensemble members I have. And thereby doing, I populate a histogram like this one. So on the top, I'm showing that the probability that the maximum in orange or minimum weakest in blue transport happened in any given year, okay? And what I want to draw your attention to is if you look to the far right, so we're showing the probability essentially on the y-axis and time on the x-axis. I want to draw your attention to the far right of the plot where you see this collection of high blue bars. What this is telling us is that there's about a 75% chance that the weakest decadal transport, so these are decadal averages, the weakest decadal transport probably happened in the past 2 decades or so, okay? And that can't be attributed to decadal variability. Why do I say that? Because that's what I'm quantifying on the plot below. So the plot below is the same histogram, but what I've done is I've removed the long-term trend that I showed before. So in other words, if this weakest transport was due to decadal variability, in other words, not the long-term trend, we should still see that stacking up of histogram bars on the far right near 2010, but we see that that doesn't happen. In fact, in this case on the bottom, it's unlikely that the weakest transport happened in the past 2 decades. So we conclude that this is another sign of the gradual weakening of the current over the past century or so. So that's the main result of my analysis, that no matter how you slice it, it looks like the Florida current transport has weakened steadily over the past century. Here we get into a little bit more uncertainty when I ask the question, why? Okay, what does weakening of the Florida current transport tell us about the large-scale circulation? In other words, or you can say this otherwise, what caused this decline? Okay, and as I said before, we want to think of mass or volume conservation. If we imagine the North Atlantic 27 north, so we're going from, in our sort of little mental sort of picture here, we're going from Florida on the left, across the Bahamas, the whole way across the Atlantic to Morocco and Northwest Africa here on the right. If we have a slowing down of this circulation in the Florida Straits, something else must have slowed down also. It could be the deep overturning, the deep return flow, which is what we're interested in primarily, but it could also be a change in the wind-driven gyre. Remember that the Florida current, in sort of simple theories, the Florida current is essentially the return flow for the interior gyre. So it could very well be that there is no change in the deep return flow, and that all of the slowdown of the Florida current is related to changes in the spare drip transport. So I wanted to test that. I went to test that looking at wind fields because, of course, the interior spare drip gyre is directly related to wind stress curl. So 2 plots here. I'm going to look at 2 gridded reanalyses of the 20th century, okay, and I'm going to compute changes in the spare drip stream function. This is quantifying the transport of the interior gyre. The first plot, the one in the middle labeled panel A, this is the time average over a 110-year period, okay? The blue is an estimate based on a NOAA reanalysis product, US product, and the orange is based on an ECMWF reanalysis product from Europe. Okay, so these are just 2 different data sets of wind stress. Okay, the thick lines are the geostrophic stream function, but I'm also showing these thin lines, which are the geostrophic plus ageostrophic Ekman component, just to give a sense of the importance of that ageostrophic term. Again, these are time means, and this is more or less a sanity check. Okay, so we're showing latitude going from 10 north to 50 north on the y-axis, and transport and sphere drips on the x-axis. So negative values are south, positive values are north. And if we look at the mid-latitudes between, say, 25 and 35 north, we see more or less what we expect. We see a general southward gyre transport on the order of 20 to 25 sphere drips. Okay, so again, that's consistent with other measurements, and again, it's more of a sanity check, and it shows that these two estimates are in pretty good agreement in the time mean. If we look to the right, I'm showing the same thing, but now I'm not showing the time mean of the stream function. I'm showing the trend in the transport. Okay, so again, orange is the European product, blue is the NOAA product. Again, the thick line in shading is the geostrophic. The thin line in the dashes is the geostrophic plus Ekman. And really, I mean, again, there's a lot of details here, but what I really want to, this glaring result I want to draw your attention to is, again, between about 25 and 35 north, so our subtropical region, these two estimates don't even agree in terms of sign. You have these apparently significant values in the orange that are negative. In other words, the ERA product suggests that there's a spinning up, an increased southward transport, whereas the NOAA product suggests this northward anomaly, that is a slowing down of the transport. So long story short is, based on these reanalysis products, I'm not even able to say anything about the sign of any possible change in the transport in the gyre. Here's another view of that. You know what, in the interest of time, I'm not going to dwell on this too much. Suffice it to say that the conclusion here is that, like before, this result, that the two disagree, isn't sensitive to the particular time period. If you pick any multi-decadal period of the past century, you get this really glaring difference between the products. But I want to get on to make sure I don't miss anything here. Bottom line is, I really can't say anything about the gyre, but don't worry. Still an interesting story to be told. Remember, I'm interested in the overturning circulation. There are these past hypotheses based on proxies that the deep return flow of the overturning has changed. And some of those, particularly the paper by Cesar and earlier studies by Stefan Rahmstorf and others, make the hypothesis that the deep return flow has weakened based on this notion of a warming hole in the North Atlantic. So here I'm showing trends over the past 110 years in sea surface temperature. Okay, I've removed the global average time series, so these are sort of deviations from the general global warming. But what I want to show you here, again, colors indicate the SST trend. Blues are cooling, yellows are warming relative to the global average. I'm using, again, these gray stipples to indicate where things are not statistically significant. But there's this really conspicuous region in the northern North Atlantic, in the subpolar region, which I've outlined here in black. This is what previous authors have called the warming hole. It's regions where SST has declined relative to the global mean fairly steadily over the past decade. So here's the time series of SST over that region. The black is the average of a few different SST estimates, and the colored curves are SST from individual products. Unlike the analysis with the winds, you get very good agreement between different products. They're not entirely independent. You know, a lot of these products are based on the same underlying data sets, but you're getting some sense of uncertainty here. So what we have is, in this warming hole region, a decline in SST on the order of minus 0.6 plus or minus 0.4 degrees Celsius per century. Again, the plus or minus are 95% confidence intervals. Through a little bit of physics, you can translate that SST trend. If you assume nothing else changes, if air temperature doesn't change, wind speed doesn't change, you know that cooling of the surface implies a heat flux. In other words, if the SST is cooling, you must be drawing down heat into the ocean. So if you do that math out, you find out that this SST alone implies a centennial trend in surface heat flux of 16 plus or minus 11 watts per meter squared per century. So that's how much is implied coming into the ocean. Even though it's a warming hole, it implies that heat is going into the ocean. And if you imagine that heat is just stored locally, okay, so you have heat entering the ocean, and you imagine that stored locally, just say it's stored locally in the North Atlantic, north of 27 north, which is where our Florida current is, north of 27 north, but between there and Bering Strait, so the northern North Atlantic and the Arctic Ocean. If you imagine that heat stays there, you'd get a sort of a total warming of the North Atlantic, full depth, of about 0.4 degrees Celsius over the past 110 years. And we don't observe that, okay? So what must be going on? Well, it must be that if you have this heat flux through the surface, that it's not being stored locally, but that it's being compensated by a heat transport, okay? So we're appealing to the notion here of heat conservation. So remember, we started saying, let's consider mass conservation. Now we have a new constraint, which is heat conservation. So I'm going to do a little bit of math now that might help us out. Okay, so I'm going to state things in equations now. So mass conservation across 27 North, I'm giving as this top equation here, where I'm using psi to mean, or psi prime rather, to be the trend in different transports. So psi f is the Florida current transport trend. The psi with the d is the trend in the deep return flow, okay? And the psi with a t is what I'll call the thermocline recirculation. This includes that gyre that we're very uncertain about based on the winds I showed you, but also things like the Antilles current, which is also very uncertain. So I'm going to say that, I'm going to demand that when you sum across 27 North that you have no net change in transport, okay? That's my mass conservation constraint. I'm also going to impose a heat conservation constraint that mathematically states what I just said, that you have this heat flux through the surface, okay? That's what I'm writing on the right-hand side of this middle equation, where Q is the heat flux, A is the area over which that heat flux is acting, rho is ocean density, and Cp is heat capacity. So again, the right-hand side is that heat flux. And as I said, that's not being stored locally, but it's being evacuated by a reduction in heat transport across 27 North by ocean transport. So again, we see on the left-hand side, I'm not sure, hopefully maybe you can see my cursor here, on the left-hand side of that middle equation, we again see those psi terms, which are again the transport trends in the Florida current, the deep return flow, and the thermocline recirculation. But now they're being multiplied by temperatures, okay? Average temperature in the Florida current, the deep return flow, and the thermocline recirculation. Those are the heat transports, okay? So those are the two principles, mass conservation, heat conservation. And one last note I'll make is that you can write this air-sea heat flux, QAS, we're in the bottom equation now. Total heat flux is the sum of the short wave and long wave heat fluxes, but also the evaporative and latent, latent and sensible heat transport, some of which are functions of SST. In these equations, I know what, the reason I write that heat flux as a function of SST is I know the SST trend. I just showed you that time series. So SST is something I know. I also know the psi prime f, that's the change in the Florida current transport. What I don't know psi prime d. This is the thing we're really interested in. This is the trend in the deep overturning circulation. And I also don't know psi prime t, which is that trend, if there is one, in the thermocline recirculation. I can manipulate these equations, do a little bit of algebra, to solve for the things that I don't know in terms of the things that I know. Okay, so here are the manipulated equations here on top. So the first one is the equation for the deep return flow of the overturning. So again, it's that psi prime d. And I'm writing that on the right-hand side in terms of things I know. I know the change in the Florida current transport, psi prime f. I know the SST trend, SST prime. All of these thetas with bars are time average temperatures, which I know from, I could look at something like the World Ocean Atlas. And all the coefficients in front of the SST, the A, Cp, and rho, these are just standard constants. And this symbol I've written, capital gamma, which I define below, is also something that I know based on the background state, things like winds and SST. Okay, so I can compute psi d given everything on the right-hand side. I can do the same thing for the thermocline recirculation, which again, that includes the sphere drip gyre, and it includes the Antilles current transport. And these are the results I get if I actually plug in the numbers. So let me explain what I'm showing here. So the top plot is for the deep overturning. The bottom plot is for the thermocline recirculation. And what we're looking at isn't a time series, but it's a time series of trends. Okay, it's a time series of trends starting at the year indicated. Okay, so for example, 1910 or 1920, and extending all the way to 2018. So the top plot shows the trend in the overturning from 1909 to 2018, all the way up to 1980 to 2018. And what I want you to notice is that, so the thick bars is the mean, the dark shading is plus or minus 1 sigma, the light shading is plus or minus 2 sigma. What I want you to see here is that for most of the first half of the 20th century, from about 1910 to 1950, you get values that at least to 1 sigma or so are positive, are distinguishable from zero. So remember the sense of the deep overturning. It's flowing south. So a positive anomaly means a slowdown. Okay, so for basically for multi-decadal periods, say starting in 1950, all the way to centennial periods, starting at 1910 to present, we detect a marginally significant weakening of the overturning. Once you get to shorter periods, more recent than 1950, the uncertainties grow a bit and we're not able to say too much. Okay, but the results do support a weakening of the overturning since about 1950 in times earlier. When we do the same calculation for the thermocline recirculation, we get much, much bigger uncertainties. These are on the same scale bar. The lines indicate the same thing, but you can see that everything is much more stretched out in the vertical, meaning much more uncertainty. Long story short is we can't really say anything about the thermocline recirculation. Okay. Why are these uncertainties so different? Why can I say something more certain about the deep overturning, but not the thermocline recirculation? Well, it has to do with ocean temperature stratification, namely the fact that vertical stratification in the ocean is much stronger than horizontal stratification. So here's a cross-section of the Atlantic, going from Florida all the way across to Western Africa. Here's the mid-Atlantic ridge here in the middle. And so blues are colors down near 0 Celsius, yellows are colors near temperatures near 30. When you compare the Florida current flowing north through the Florida Straits to the thermocline recirculation gyre flowing south, you see that they're acting on very similar temperatures. Okay, in other words, the heat transport is not very sensitive to changes in these two currents. So knowing the Florida current transport doesn't really tell us much because this temperature gradient is so small, it gives a lot of leeway to the possible history of the thermocline recirculation gyre. On the other hand, the temperature gradient between the Florida Straits and these deeper, colder waters that the deep overturning is acting on is much greater. So it much more tightly constrains what the possible history of the deep return flow could have been in order to achieve heat balance given the Florida current transport and that heat flux. Okay, so the reason I can say something about the deep overturning but not about the thermocline recirculation is due to the much stronger vertical compared to horizontal stratification of ocean temperature. And with that, I'll wrap up. Again, I'll re-show my slides from the beginning. Again, there's a lot of details there, but if you walk away with nothing else, know that these observations support a steady decline in the Florida current transport over the past century. This observational result, based on instrumental data, corroborates independent hypotheses based on proxies that the deep return flow of the overturning declined over the recent past. And it also, remember those climate modeling results I showed you way at the beginning. What I find here supports simulated relationships in climate models that say when you have a change in the deep return flow of the overturning, you tend to get a similar change in the western boundary current. Okay, that was a lot in a small amount of time. I know I breezed through some of the things and maybe didn't describe all things as well as I could, but if you're interested in this, the paper did come out a couple of months ago in Nature Communications. It's open access, so do feel free to download it, give it a read. Let me know what you think. With that, I'll take questions. Thank you very much.
Thank you, Chris. Chris, we have a tradition here that we let the students to have the first shot at questions before the faculty members start using up all the air in the room. And so if any of the students have questions, everybody, I've got the participants list on and I can see if you raise your hands. You should pop to the top of my screen. So any students have any questions? Well,
I see one hand.
Yeah. So we'll go ahead then. If any of the students, if you have a question, you think of it, pop your hand up and I'll put you to the front of the line. Go ahead, Digna. Digna, you're still muted.
Hello, can you hear me?
Yes.
Yes.
Go ahead, please.
Hi. You know, from the data that you were showing, like in the middle of the presentation, that you showed some histograms and trends, with cable data and other type of data. And of course, the newer data has much less, how you say that? I mean, it's more defined, and all because you put there the cable data. So you know, when you compare that with older data, it's kind of hard to tease out how much of what is happening now happened or not in the past, because now the data doesn't have as much how we would call it dispersion. So I was thinking, had you considered to degrade the newer data, like for example, not using the cable data, which is the one that gives more detail to the data, and see how it behaves compared with the past?
That's an excellent question. So again, just to excuse me, to repeat, a very good question. Digna asks about how dependent the solution is on the modern data. What happens if you imagine degrading the data or withholding some of the data? Well, I can't go all the way. Like I can't entirely remove the Florida current transport data because then there's nothing to work with. There's nothing to calibrate my tide gauge measurements all. So I have to include some cable data. Okay, but we can play some games along the lines of what you suggest. We can imagine doing a couple things. One is omitting data. So as part of the paper, and this is all just for ease of the slides here, I can show it if you really want, but I'll just keep my screen on myself here. I did one experiment where I withheld half the data. Okay, so remember the cable data go from 1982 to the present. I withheld the first 20 years of the cable data. Okay, so as one would imagine, the estimate between 1982 and 2000, when you withhold that cable data, the reconstruction becomes more uncertain because you've withheld that data. But in terms of the things that we're interested in other words, what is the probability that the transport declined, you don't see any real change in that statistic. In other words, you find out it's just about as likely that the current declined if you only give the algorithm half the data as all the data. You can play a similar game by increasing the standard errors. You know, imagining the data are poorer than they actually are for the transports and rerun that through the Bayesian algorithm. The same thing happens. You get slightly larger uncertainties for the recent decades when you have data, unsurprisingly. But for the past, which is what we're really interested in, for those long-term trends, there's no qualitative difference. Those histograms get a little bit wider. But again, if you're asking questions about the sign, did it decline or not, those statistics are relatively robust. So, and I detail that in the supplementary if you're interested in the nitty-gritty details. But that's an excellent question.
Thank you very much, and it would be nice if you put the link for the paper in the chat.
Yep, I'll do that. Yep, happy to do that.
Thank you, Chris. Boyceberg.
Chris, well, thank you for a very nice seminar. You should know that when I was a graduate student at URI, I also fitted with biology for a semester and decided to go back to physics. So good choice. So, you know, relating this decline in transport to the deep circulation and relative to the long time scale of the decline makes a lot of sense because at some point this fluid has to come back up and takes a long time to do that. So with that as a background, do you care to comment on what this may imply with regard to anthropogenic versus natural variations in climate?
Yeah, great question. So before I start answering, I do want to acknowledge, so Digna, I did put the link to the paper in the chat. So anyone who wants to be directly linked to the paper, it's sitting there in the chat. Yeah, no, so Bob, your question is really, really interesting. You know, as you hinted in the lead up to your question, there certainly is a time scale dependence to this problem. You know, you're not going to expect necessarily a change in the Florida current transport to be mirrored by a deep overturning change in, I'll say, annual timescales. In fact, if you look at the rapid data, because they sort of break down some of these components, if you look at the raw rapid data, you do get a pretty strong anti-correlation between that interior thermocline recirculation that I mentioned and the Florida current transport. So it suggests a very different physical regime in terms of what RAPID is observing versus what I'm showing here on the longer timescales. But you ask a really good question. You know, I haven't attributed, you know, what's driving this decline. I don't know, but it does have real implications for the question you asked, which is it anthropogenic? That's really hard to tease out. I mean, I'm going to think out loud here. You know, it doesn't. There's no smoking gun here, but I mean, it leans more towards it being not an anthropogenic thing. I mean, the anthropogenic forcing has ramped up over the past century, and from again, the uncertainties are large, so one has to be careful what stories can and cannot be told based on this reconstruction. But it's not obvious to me that there's any real acceleration, you know, in that decline. So, you know, I have to ask questions about, you know, what happened earlier. You know, there are lots of there's a lot of uncertainty still and interesting stories about, you know, what happened to the large scale circulation at the end of the Little Ice Age. You know, there's been nice sort of work on this by David Thornalley and others, and raised a lot of interesting questions. And we don't really know. You know, we have this conundrum that, you know, at the same time that some of our oldest instrumental records are going online in the mid 1800s, you've got the end of the Little Ice Age and the start of the Industrial Revolution. And there's just, you know, one has to wonder, you know, how many degrees of freedom are there and to what extent can you separate all these different physics? But anyway, it's a long babbling answer to, you know, I don't think it really paints a clear picture of a strong anthropogenic influence on the Florida current, at least in this case.
Good, thank you. My interpretation is kind of like yours, and it points to the idea that there's a lot going on that we still don't understand, and there's a lot to learn. So for all the students out there that haven't asked a question yet, there's plenty more for you to do throughout your career. Thanks.
Oh yeah, no, I agree with that. And just to second what you just said, Bob, and I'm reminded of conversations I was having with the students at noontime. I mean, this is really, I think, you know, I noticed there's a lot of PO students in the department, and there's a lot of folks doing sort of paleoceanographic type research in the department. And there's a lot of room for the two to really collaborate here, you know, on these questions of centennial to millennial scale change in the common era, and how do we put, you know, essentially, you know, my paper is one data point. How do we put this centennial trend into the context of, say, just, you know, the last 2,000 years or the late Holocene or something like this? There's a lot of work to be done. So I encourage the grad students on that front.
Okay.
And along those lines, we need all the students we can get in physical working on these sort of things. So if any of our biology students want to switch, I'm sorry, my biological colleagues are shaking their fist at me now. Okay, Fred, I think we'll take one more. We're 10 minutes over, so I think we'll take one more.
Okay, hi, Chris. Real quick, do you think that the trend will continue? And if so, what do you see as the ultimate climate/weather implications for the north of Europe? I have a summer place in the Baltic Sea, and so I'm interested in if it'll get hotter or cooler over time.
Yeah, no, that's a cool question. You know, I've been so focused on the past here. It's one of those, oh man, well, that was obvious in retrospect. I haven't probed that. What's nice, though, is that, you know, with this, I could give you an answer. What's nice about this Bayesian reconstruction is that I was showing these time series of the transport, right? And I emphasized, hey, I've got this whole ensemble of thousands of estimates. What I also have is a data constrained model. I didn't go into too many of the details, but this model is a set of equations, right? And it's equations for how the physics evolves and how the observations relate to the physical processes. And those equations have these physical parameters. Again, things like spatial covariance scales or autocorrelation timescales, trends, and all of this. So you can kind of think of it as this little data constrained model in a box. Okay, so what I could do is take those data constrained solutions and sort of run them forward under random forcing in time. Essentially, the model is forced by random perturbations. Okay, so I could basically take these solutions and run it forward in time and see what it predicts into the future, or to what extent, you know, the uncertainties completely blow up. I don't know, but it would be a quick and easy exercise to do given the data, and I could let you know whether or not you should be selling that property anytime soon. But yeah, don't have the answer right now, but great question.
Awesome, thank you.
All right, so thank you all very much for coming. I invite you now to turn on your microphones and applaud Chris.
Thanks, everyone.
Thank you very much, everyone. Chris, that was great. If you would, Chris, if you wouldn't mind, just stay on a bit after people go,
Yeah.
and I'll talk to you for a moment.
Yeah, happy to. Thanks, everyone. I appreciate it.
I'll be right back.
Thanks for the talk.
Thank you.
Hey, Chris, I'm sorry I missed the little physical oceanography gathering early in the afternoon. I was tied
No
up.
worries. That's
Um,
understandable.
So, I did a reading class with my students, I guess it was last year, and we looked at, different indices of climate variability and different modes of variability, starting from ENSO and then going along the timescales. And what became very clear from the literature is that none of these are independent from one another. It's a highly nonlinear process, and the ocean basins themselves are related. And the longer term variability, it all seemed to point back to the North Atlantic. And so I think what you're doing is really, really fascinating. I've always been, if you look at the northern part of the subtropical gyre, there's a region where the heat flux from the atmosphere to the ocean is very large. And I'm sorry, the other way around. And if you then look at the equatorial region, it's of an opposite sign. And so while nobody's really discussed the mechanism, the linkages between those two very large air-sea interaction regions, that's got to somehow be involved also in a longer timescale kind of variation. Anyway, I think what you're doing is kind of neat, and I enjoyed your talk. And
Thanks.
I'll give you back to Gary and say thanks again.
Yeah, my pleasure. Thank you.
Okay.
Have a good weekend. So Amelia sent me an email while we were going, so she had to step away. So she handed it off to me. So I'm sure sorry she didn't get a chance to meet you, but
well, that's okay.
But maybe we do have we sent you an invitation for the.
Yeah, saw that.
So
yep.
it's a toss up every week as to whether one person shows up or none or 10. So, but I will be there. So if you can, please, but don't feel like you have to, whatever you need to do.
Yeah,
anyway,
no, I'm happy.
Nice. Let me read you one thing. I got an email. About halfway through the seminar from one of the students saying, actually one of our postdocs, research associates, saying, wow, this guy really explains things really well. So anyway, congratulations.
Awesome.
Very good feedback. Okay.
Excellent.
All right. Well, I'm going to hit the head and I'll be back on at 5. If I see you, if not, thanks again. I really appreciate
my pleasure.
Your coming down, so to speak.
My pleasure.
Hopefully, maybe in a year or so, we'll have time for a real meeting. So it'd be great to have you down just to spend a day or two just talking about